Hello friend, in this discussion we want to discuss a number on combined twisting and bending moments. With one example in each case, explain the following types of shaft. Roman 1, transmission shaft. Roman 2, machine shaft. Part B, distinguish between equivalent twisting moment and equivalent bending moment. Part C, we have a question that says a solid shaft is subjected to a bending moment of 3000 Newton meter and a torque of 10,000 Newton meter. The shaft of 45 C8 steel having ultimate tensile stress of 700 megapascals and an ultimate shear stress of 500 megapascals. Assuming a factor of safety of 6, determine the diameter of the shaft. Let us look at solutions. So this is a Roman 1 and this is Roman 2. Transmission shaft are shafts that transmit power between the source and the machines absorbing the power. An example is the counter shaft, the line shafts and overhead shafts, and all factory shafts actually are transmission shafts because they carry machine parts such as pulleys, gears, and therefore are subjected to both bending and twisting moments. Machine shafts are shafts which form an integral part of the machine itself, and an example is the crankshaft because it forms the integral part of the machine, and that is an engine. Now let us look at differentiating between equivalent twisting moment and bending moment. Equivalent twisting moment is defined as that twisting moment which, when acting alone, produces the same shear stress as the actual twisting moment, while the equivalent bending moment is defined as that moment which, when acting alone, produces the same tensile or compressive stress as the actual bending moment. Let us look at part C of this particular number. Now, given the data, the information is bending moment is 3000 Newton meter, the torque or the twisting moment is 10,000 Newton meter. The ultimate shear stress tau u is 500 megapascals, and we can also take it as 5 exponent 6 pascals or Newton per square meter, and the ultimate tensile stress sigma u is 700 megapascals or 700 times 10 to the power 6 pascals or Newton per square meter. The factor of safety is given also as 6. In the design, we are going to use the allowable working normal stress. The allowable working normal stress leading to bending is therefore sigma b equal to sigma u, which is the ultimate tensile stress, divided by the factor of safety Fs. So this is equal to 700 times 10 to the power 6 divided by 6, and this gives us 116.667 times 10 to the power 6 Newton per square meter. The allowable working shear stress also tau is equal to the ultimate shear stress divided by the factor of safety. It is this allowable working stress that we are going to, the allowable working shear stress is the one we are going to use in the design of our shaft. So it is equal to tau u divided by Fs, which is the factor of safety, and substituting in those values, we get tau, the allowable working stress, as 83.33 times 10 power 6 Newton per square meter. Now, from the maximum shear stress theory, or what we call Tresca's theory, we know that pi d cubed, or pi times the diameter, the outer diameter cubed, divided by 16, or just diameter if it is a solid shaft, times the allowable working stress, shear stress, is equal to the square root of m squared plus t squared. This is the bending moment, this is the twisting moment or torque. So if we make d cubed the subject of the formula and substituting in our values, we get something like 16 divided by pi times 83.33 times 10 to the power 6 times square root of 3000 squared plus the square of 10,000. And simplifying that figure would give us the diameter according to the maximum shear stress theory as 86.9 millimeters. Case 2, if we consider the maximum principal stress theory, or what we call the Rankines theory, we shall say that pi divided by 32d cubed, or the diameter cubed, times the bending stress is equal to m, or the bending moment out of 2 plus half of the square root of the equivalent twisting moment, or just a half of the square root of a bending moment squared plus twisting moment squared. So if we substitute in the values given to us, d cubed is equal to 5.8672 times 10 to the power negative 8, and when we take cube root of this figure to get d, then the diameter d is equivalent to 83.7 millimeters. Now, considering the two failure criterion, we have gotten a figure of 86.9 millimeter and a figure of 83.7 millimeter. Therefore, we have to take a diameter, a figure which is bigger. So the diameter which is bigger, or the larger one, is the one chosen to avoid or to prevent failure from both criterion. Because if we take 83.7, then it means by shear stress theory, the shaft will have to fail. But if we take 86.9, it means both the shaft will be protected from the failure criterion of both maximum shear stress and the maximum principal stress. Thank you so much for